Hi, Max. Is this question, why are the Bragg's laws different in 3-dimension and 2-dimension? Okay, so the short answer is a little complicated. So I'm going to give you the long answer, and then you can figure out how to make it short. So this is the 2D Bragg's law. The 3D Bragg's law has a 2 out here, so 2D sine theta equals n lambda, or d sine theta equals n lambda over 2. Same thing. So the factor of 2 is missing because we are working with one less dimension. Now, what does that mean? Now, to help you to understand what that means, I'm going to show you this picture here. This is the derivation of the 3D Bragg's law. So conveniently, they show you how they derived the 3D Bragg's law, but they don't show you how they derive the 2D Bragg's law. So I have drawn this out here. I've copied this here. So I'm going to use a little circle here to point to stuff. All right, so this is a 3D crystal, and some light is coming in at an angle, and it's hitting the crystal, and some of that light hits the top particle, and some of that light hits the bottom particle. All right, so the light gets scattered in all directions, and one of those directions is this direction. Here, the light gets scattered in all directions, and one of those directions is this direction. All right, so the light that is coming off of here is going to interfere with the light that is coming off of here, because this distance is very small. This distance is very small because this distance is very small. By very small, I mean it's comparable to the wavelength. It's that kind of small. All right. So now, what the important thing is that in order for us to see, us or the detector, in order for us to see a bright spot, is this piece of light has to be in phase with this piece of light for constructive interference. If there's destructive interference, we're going to see a dark spot. If there's some combination of destructive and constructive interference, we're just going to see some fuzziness. So we need to have constructive interference. Now, for constructive interference, this guy has to be in phase with this guy. That's hard to do because this guy traveled a certain distance. This distance and this distance. But this guy traveled a longer distance, this distance and this distance. So the extra distance that this guy traveled has to be equal to either 0 or 1 full wavelength or 2 full wavelengths, etc., in order for this guy to still be in phase with this guy. So there has to be an integer number of wavelengths in the extra distance that this ray traveled. And what is that extra distance? That extra distance, let's see. So these guys are coming in, and right at the dotted line, the bottom ray has to travel extra distance. Bounces off, and right at the dotted line, the bottom ray is finished traveling its extra distance. Now, it is on a par with the top ray, right? So the extra distance is fully defined by this segment and this segment. These two segments are equal, as you can see here. So we really just need to figure out the length of one of these segments and then multiply it by 2. So that's where the 2d sine theta comes from. This is theta, and this is d. D is the hypotenuse, right? The distance between these two particles is actually the hypotenuse of this triangle with theta as one of the angles. So d sine theta would be this length right here. So 2d sine theta would be both of these lengths together. And these represent the full extra length that this ray had to travel. Now, that 2d sine theta has to equal an integer number of wavelengths. So that's why Bragg's law is 2d sine theta equals n lambda. Now, what about if it's 1d? If it's 1d, then we are not bouncing something off the top and bouncing something off the bottom, because there is no top and bottom. It is flat. So, to help you to see that, I'm going to rotate this. Okay, so there is no bouncing, so I'm going to start erasing. So we are not bouncing. Oops, wrong color. I gotta erase. All right, so we are not bouncing anymore because there's nothing to bounce off from. There are no layers to bounce from. This is a 2D thing, right? Right? And since it is a 2D thing, of course, there's only one layer, so there's none of this. This doesn't exist. This doesn't exist. This doesn't exist. This doesn't exist, right? So what is this? So okay. So what is this? This is no longer the crystal plane. This is now the path of your incident laser light. So your laser light comes in here, yeah, and your laser light comes in here, and it gets diffracted. It gets scattered in all directions by this particle, and there's another. So these blue, so my white dots here are just replicas of these blue particles, and this is a my black line here is the microscope slide that these particles are all sitting on. Okay, the laser is coming into the microscope slide, and they are getting scattered in all directions, by these by the nuclei of these crystal of these particles. And one of those directions is this direction, and for this one also one of those directions is this direction, and the angle by which this ray is getting deflected from the straight path of the laser is theta, right? So there's a screen here, of course. In your experiment, there's a screen here, and we will see a spot or a piece of a bright ring right here if constructive interference happens between this guy and this guy, right? So we need constructive interference to happen there, and then these we have a in your lab manual they call this length the big R, distance from the microscope slide to the screen, and they call this the little r right here, distance from the center of the circle or imaginary circle on the screen to the ring or the dot on the screen. All right. So we calculated this theta using the arctangent function, and then you could see that this ray of light, it doesn't bounce off anywhere, so we don't get two extra lengths. We just get one extra length. This extra length, let me outline it here. This is the only extra length that we get. All right, so this ray of light gets, let me get bigger here. All right, so this ray of light gets scattered in many directions, and this is one of the directions. This ray of light gets scattered in many directions, and this is one of the directions. But from here to the screen is the same distance, the same length as from here to the screen. But there's this extra length here. This extra length needs to be a multiple, an integer multiple of the wavelength if you want constructive interference to happen here, all right? And what is this extra length? This extra length is nothing more than d sine theta. So that is why there is no factor of 2 in the 2D Bragg's law, while there was one in the 3D Bragg's law. Man, what a brainstorm, huh? All right.